Welcome. I'm Jillian Gregg, and I'm an ecologist here at Terrestrial Ecosystems Research Associates. And we have rented the EPA chambers in order to be able to do a global climate change research project. I'm going to be helping you visit our project through your e-course. So even though you can't be here on this sunny day, I hope it's not raining over where you are, but it's quite nice at the moment. So the basic idea is that with global warming projects, most of all of the global warming projects that have been performed have looked at equal increases in temperature throughout the day and night. And that's because policymakers have been interested to know, well, actually, how much warmer is the globe going to be? So climatologists have gone to every climate station throughout the globe and said, how much has it gotten warmer, and how much do we expect to get the whole globe to get warmer? And so on average, climatologists have said, we expect there to be a range, between 1 and 4.5 degrees warmer by the year 2050. And so ecologists have taken that and said, okay, well, we need to know then if temperatures could get that much warmer, then how might ecosystems respond? And so they've taken a mid-range value of about 3.5 degrees Celsius and said, okay, what will the ecosystem do if you made it 3.5 degrees Celsius warmer? So there's many, many research projects that have used around that temperature increase to look at potential impacts. Now, the problem with this is that when climatologists look at the data a bit closer, they see that the minimum temperatures, the minimum daily temperatures, have gone up at a faster rate than the daily maximum temperatures. And so that means that the nights are getting warmer than the days. So if you're a plant, I might just ask you, I'm used to giving these tours and asking you questions. So if you're a plant, do you know what would be the difference in the day and the night? And so I guess I'll be answering your question too, as that certainly plants photosynthesize in the daytime. So when it gets warmer, they're going to have it, they may increase in photosynthesis and therefore help to offset the elevated CO2 problem. Whereas when temperatures get warmer at night, plants are no longer photosynthesizing because there's sunlight. So the primary physiological response is respiration, which releases CO2 back into the environment. So if instead of having equal increases in temperature throughout the day and night, like most experiments have done, we actually have a greater increase in nighttime temperatures, then it's possible that we have a higher respiration rate. And so instead of helping to sequester more carbon and bring it out of the atmosphere, then we may be respiring more CO2 and then thereby compounding the elevated CO2 problem. So when we began this experiment, no one knew what might happen. In fact, ecologists were divided. There were two camps. One camp said, well, let's see, with the warmer minimum temperatures, well, you're going to have a less frost-free, you're going to have more frost-free days. And with more frost-free days, you should have a longer growing season, and the plants should all grow more. And it turns out that if you look at the satellite images of the last century, or tree rings, or crop yields, all of these different indices of plant growth show that plants, in fact, are growing more. And so folks think that could be because you have the longer growing season, because you have these warmer minimum temperatures. But then there's this whole other camp, and they've been performing growth chamber experiments and models, and using models to predict what would happen. And for those, whenever you make the night temperatures warmer, in every single case, the plants grow less. And what's happening is night temperatures are warmer, and so you have higher respiration, and therefore you get less growth. And so there's these two completely opposite camps, and who's to say what might happen? So that's what we propose for the project here at the EPA facility, is to look at the impacts of to really perform these asymmetric temperature profiles. So and see what happens. In order to perform such an experiment, you need a precision climate control facility where you can measure the photosynthesis and respiration throughout the day. And that's exactly what the EPA built and that was utilizing in the 90s and was available to determine the impacts of asymmetric versus symmetric warming, we perform an experiment. So the chambers that we were renting for the EPA, there's 12 different chambers. So within each chamber, we're able to control the temperature, humidity, and CO2 concentration. So what we have is outside, there's a weather station. I don't know if you can see that. So tower over here tells us what the temperature and the CO2 and the relative humidity are outside. And then here's our chambers. And in the chambers, each chamber has a miniature weather station where it's telling the temperature and the CO2 and the relative humidity. And those different parameters are all fed into mission control, which we'll look at later. And the chamber is able to control all of those parameters to be the same as outside or a different temperature. And so there's 12 chambers, and 4 of them are our control chambers, and they just make the climate be exactly the same as outside. 4 of them are symmetrically elevated temperatures, so they're 3.5 degrees Celsius warmer every minute of every day throughout the whole experiment. Then there's 4 chambers that have a treatment that we call asymmetric warming, where they're 5 degrees Celsius warmer at dawn, and that changes minute by minute throughout the day, so midday when they're only 2 degrees warmer, and then back minute by minute till the next dawn when they're 5 degrees warmer again. And that's what we call our asymmetric warming treatment. So both the asymmetric warming and the symmetric warming are warmer by the same average, 3.5 degrees Celsius, but they're giving those temperatures in different patterns where the warmer temperatures happen at night for the asymmetric treatment. Okay. So in order to begin such an experiment, there was no ecosystem. So we actually spent a couple of years getting ready to begin the experiment. So first we had to revamp the chambers. There's a whole, in addition to what you see here, where it's 1 meter by 2 meters on a footprint and 1.5 meters to a little bit more than that tall, they also go 1 meter into the ground. So we went to a local grassland that hadn't been disturbed for the last 100 years, and we were able to excavate the soils horizon by horizon and back-layer them into the soil. And you'll hear more about that when we talk with Virginia about her experiment. Then the grassland species we raised from seed in the greenhouse and planted out on a grid, and we'll be able to show you pictures of that later also. But they're all native Willamette Valley upland prairie species, and we have grasses and forbs and annuals and perennials and end fixers and non-end fixers. So we can say as these different treatments are provided to the grassland, which species will prevail, which ones will die out. And because we have 14 species, they also have a range when they flower and when they don't flower. And so we can see if there's changes in the flowering time with the different warming. Okay, so now we're in front of one of the chambers. This is one of the asymmetric treatments. And as I said before, there's 12 chambers. 4 of them are asymmetric, 4 of them are symmetrically warmed, and 4 of them are the same as ambient. In this one, you can see it's 2 meters on a footprint, 1 meter back deep, and it's a 1.5 meters to 1.8 meters tall, roof sloping, and it goes 1 meter into the ground where we have all the soils replicated from the grassland ecosystem also. So you can see we have a range of 14 different species in here. You're not going to be able to see them all. We have a couple that are flowering currently. So the yellow flower in the back is Portentilla, and the purple flower in the front is Sedelcia. One of the main grasses is the bromus, and you'll probably see a slide that shows all the different 14 species that we have. But we have a range of grasses and forbs and annuals and perennials and end fixers and non-fixers that we can see which ones come to predominate and which ones go extinct over the course of our experiment. Okay, so now we're in front of an ambient chamber, and you can see that the biomass is much lower in this chamber. It also has more of these purple flowers, the Sedelcia, and and now we're in front of a symmetrically elevated temperature chamber. And you can see this one is not quite as tall as the asymmetric one, and it's also begun to brown out. And it turns out with the symmetric warming, because you have the warmer daytime temperatures, you have more evapotranspiration, and so they're running out of soil moisture sooner than asymmetric. So in comparison to, so what we see in these moist years is that asymmetric goes the most, symmetric is next, and ambient grows the least. Okay, so the way the chambers work is that there's a miniature climate station inside each one, and then there's a large climate station outside that tells what's the ambient temperature, humidity, CO2 concentration. And then each chamber is trying to control the temperature, CO2, and humidity exactly the same as outside, or the same as outside plus warmer, either the symmetrically warmer pattern or asymmetrically warmer pattern. So I'm going to show you a little bit about the sensors and how a chamber can actually do that, because here you are in this plastic bubble on a big, nice sunny day, and we're saying it's really the same temperature as ambient. And actually, it really is. So the way it does that is here you have this chamber. Maybe if you come around to the side, you can see that there's this air handling unit on the back. So each chamber has this silver air handler in the back. So there's a big fan inside, and it blows, cools the air out of the bottom of the chamber, and then through this channel, and then back in the top. And that circle happens 12 times per minute. And while the air is in this handler, there's a big chiller. And like on your car, a big radiator, and it has cold water going through it. And as the cold water is going through there, that condenses water out of the air, which cools it. And so it dehumidifies it and cools the air. And as that happens, the air then goes back in and it's cool enough. But also inside here, we have a strip heater. And the strip heater then heats the air back up either to be the ambient temperature or an even warmer temperature. And that's how we control the temperature. But humidity, as I said, the chiller, in addition to cooling the air, takes water out of the air. Then we have a whole humidifier. And you can't see it so well, but we have a big actual steamer that you steam your clothes with, so that pumps out lots of humidity. And that steamer goes into this air handler and out, so we can raise the humidity back to be the same as ambient. And the CO2 concentration is it's monitored, and we just have a tank inside the mission control area that has a mass flow controller on it, and as it there's a CO2 monitor that they call infrared gas analyzer, and it monitors the CO2 concentration. On a day like this, when the plants are in there and they're drawing CO2 down, then the mass flow controller is adding blips of CO2 back into the chamber so that it can stay the same CO2 concentration as outside. So I'm just going to show you a couple of the sensors inside the chamber. And if you look at the one on the top, that's just a photosynthetic light measure. So it measures photosynthetically active radiation. The silver one in the middle, that is that's a climate control area around our temperature and humidity sensors. So that even though they're in